Okay, so what we're going to be looking at here is we're going to be looking at, now that we have learned how to take the derivatives of certain functions like sine, cosine, all of those other functions, like just x squared, polynomials, and trig functions basically. Now what we're going to do is we're going to start looking at how to take the derivative of more complicated functions. And what we're going to be dealing with today are what are known as composite functions on how we take the derivative of that. As a brief review as to what a composite function is, if we had f of x equals 2x plus 4, and then we had a separate function, g of x equals x squared plus 2x minus 7, and I was to ask you what is f, and the way we say this is of g of x. Remember, f of x means whatever, if I have f of 2, that is telling me that I want to know what is the y value when x equals 2. We talked about that a little bit earlier this year, so I would just go 2 times 2 plus 4. That would give me 8. That's what f of 2 would be. This right here is asking what is f of g of x. Now it's a slightly different question because it's not asking what the y value is. Instead it wants to know what would the formula be if I wanted to know what f of g of x was. The way that we would find that is we would take every x that we have in our f function, in other words the function that's on the outside, and I would put, instead of putting x there, I would put what g of x is equal to. Much like we did with f of 2 where we just replaced the x with 2, now I'm going to replace the x with x squared plus 2x minus 7. And then I've got plus 4, and that, again, is what is known as a composite function, because I've taken one function and I've put it inside of another function. If I had g of f of x, I would do the exact same thing. If I had g of 1, I would just go 1 squared plus 2 times 1 minus 7, replacing all of my x's on the right-hand side of my equation with a 1. So I'd get 1 plus 2 minus 7. That is negative 4, is what that would be. And again, this should be reviewed. That should kind of jog your memory as far as what that is. So if I had g of f of x, what that's telling me to do is take my g function, and everywhere I see an x, I'm going to substitute f into it. Okay, so I get 2 times 2x plus 4. Now look, again, we did put it in twice. One mistake that I see fairly often when people see composite functions is there's parentheses there, so people like to think, oh, that means we're going to multiply something. Well, there's no multiplication going on in this problem. It's just g of f of x, which means, again, everywhere I see an x in my g function, I replace it with whatever the f of x function is equal to. And we could simplify that down if we wanted to. That's not what we're looking at right now. We're looking at more what is a composite function, okay? Now, one other way we could say that is if I see a function that already is written like one of these, where if I just saw this initially, I'd say, oh, I know that that's a composite function because I already have a function inside of another function. In other words, I've got some function that is being squared or being raised to the 5th power or something like that, okay? In real life, more often than not, you will see composite functions that mimic real life just because it makes it so we can look at things that are slightly more complicated without having to really, delve into more complicated equations. Anyway, don't worry too much about that. Now, the issue here is, in this equation right here, I've got y equals 3x to the 3rd plus 2x squared minus 5, and that's raised to the 5th power. Right now, up until this point, the only thing that we've learned how to take the derivative of is like the 3x to the 3rd plus 2x squared minus 5 part, where we have different parts of a polynomial that are adding and subtracting together, okay? We know that the derivative would be like 9x squared plus 4x minus 5 if this 5th power wasn't here. The problem is in order for, based on the knowledge that we have right now, in order to be able to take the derivative of this function, I would have to multiply out 3x to the 3rd plus 2x squared minus 5 different times. Like I'd have 5 different parentheses, and I'd have to distribute 5 different times. And it's doable, but that would take a really, 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 really long time to do. And then we would still have to take the derivative after we multiplied all that out. Just not honestly really worth our time. And that's what that's saying right there. Now, one thing that I do want to focus on real quick is we've talked that dy dx means take the derivative. And we said briefly that as well that dy dx is also we're taking the derivative of y with respect to x. What that means is I've got some equation like this one, and when I take the derivative of that, I get the dy dx is equal to 2x plus 2. All that's saying is I took the derivative of y, and y was equal to, on the right-hand side, some sort of equation or some sort of statement that has x's in it. So dy dx, it is the derivative, but it's telling us what the variables in the derivative have to be, or the original function. Had to be a y, had to be an x, okay? So if I look at this right here, we don't just have to deal with y's and x's. If I wanted to know what dw dt was in this equation, we're saying that we're taking the derivative of w with respect to t. It's just like y's and x's. There's no difference here. The only difference is we're using different letters. It still means to do the same thing. It's still saying this is going to be dw dt is equal to 1/3 t minus 7. Okay, again, we just took the derivative using that power rule that we learned. So that would be my derivative in this case. Not a big deal, just realizing that dw dt means my original equation had a w in it, and it also, as the independent variable, had t. Okay, and that's what this is going to say right here. Now, so you might be saying, okay, well, why do I care about that? Why did you take that little tangent? Well, if I want to take the derivative of this equation right here, what I have to do is I have to have a workaround if I don't want to multiply it out 5 times. So what we're going to do is we are going to say, first of all, so if I'm looking for the derivative, I'm looking for dy dx. And keep that in mind. That's our goal, is to find dy dx in the end. Now, if I have this equation right here, I don't know how to take the derivative of it, or I do, but it would take a really long time. But let's say I wanted u to equal this inside of the parentheses part. Okay? So let's say I let u equal 3x to the third plus 2x squared minus 5. Now again, I don't know why you would think to do this initially. I'm kind of showing you the process of where this comes from. But if I had that equal my u, then I would have y is equal to u to the 5th. Now the nice thing about that is you're like, wait a minute, I know how to take the derivative of u to the 5th. That's not some composite function like we talked about earlier. It's just u to the 5th. If I take the derivative of that, I get 5u to the 4th. That's super duper easy. And you're like, okay, that made that problem way easier. But now we have an issue. Because I changed the variable from x to u, when I take the derivative of this, instead of getting dy dx, what I get instead is dy du, which is not what we're looking for. We're looking for dy dx, not dy du in this problem, which makes it a little bit more, we haven't found our derivative yet. We probably are on the right track. We wouldn't be talking about this if we didn't do it this way. But honestly, we don't have all of the answers yet. We don't know what the derivative is. Now, I want to know dy dx, and right now I don't have that. And so I have to think about this a little bit more and say, well, what do I do? Well, this next step, I don't know necessarily why you would know to do this, but if I took the derivative of what I let u equal, so I had 9x squared plus 4x is my derivative there, notice that that would equal du dx. Now, you might be saying, okay, I've got dy du here, I've got du dx here, how is that going to help me? Well, if I took dy du and I multiplied that by du dx, notice that the du's would cancel out, and what I would have is dy dx, which is exactly what I'm looking for, the derivative of y with respect to x. So I know that dy du is equal to 5u to the 4th, and I know that du dx is equal to 9x squared plus 4x. So if I just substitute both of those things in, that technically is equal to dy dx. And that, I guess you could say that that is the answer. Although for the most part, when we look at these problems, and I should probably put parentheses around that to write it correctly. If my problem started with only x's in it, if that was my original independent variable, I should probably make it so that in the end, that is the only variable that I'm looking at as well. So instead of having 5u to the 4th here, I should probably have something that has x's in it. Well, luckily for us, u is equal to 3x to the 3rd plus 2x squared minus 5. So I would just take 3x to the 3rd plus 2x squared minus 5, and then I would raise that whole thing to the 4th power. So it's almost like I'm changing it back to being a composite function again. We've got 9x squared plus 4x here. That's equal to dy dx, and that is my derivative, using this u substitution method and seeing how I could go about doing that. Now again, that is the correct derivative. Notice it made it way easier to do. I did not have to multiply everything out. I did not have to then take the derivative once I multiplied this together 5 times, which again would have taken forever to do. This is much, much easier, and that is the correct derivative, okay? So let me go through this. These are all the different steps that we take right here, okay? So, and I guess I could let me walk through these steps. I'll go through this. I didn't think I wanted to, but I'm going to, okay? So step number 1 every single time when we do these problems, now that we know how to do it, is we have to identify what our u is. In general, u is something that is inside of a parenthesis. It's the thing that's making the function be a composite function. So in this case, the fact that 3x to the third plus 2x squared minus 5 is inside of the parentheses, that makes it a composite function because all of that is being raised to the 5th power. So what we do is we choose our u, okay? So in this case, and this is what that is saying, I realize it's below the writing. Our u is going to be 3x to the third plus 2x squared minus 5 like we did before. The second step is we always take the derivative of what y is equal to. Okay, so then we get our dy du. We talked about that. We're looking for dy dx. The third step is to take the derivative of what we let u equal. In this case, du dx was 9x squared plus 4x. We talked about that before. Then what we do is we multiply those together. So really what we do when we're choosing our u every time is we look for what's in the parentheses. So in this case, let's walk through those steps again. Step number 1, I have to choose a u. I want u to be what's inside of the parentheses. So in this case, I've got 3x to the 4th minus cosine of x. So if I let u equal 3x to the 4th minus cosine of x, that is step 1. Step 2 is, now that that is the case, I have y is equal to u to the 6th. Step number 2 says we take the derivative of that, so I get dy du is equal to 6u to the 5th power. Okay? So that was step number 2. Step number 3 is we take the derivative of what we let u equal. So I've got 3x to the 4th minus cosine of x is my u. So I take the derivative of that, I get du dx is equal to 12x to the 3rd plus, remember the derivative of cosine is negative sine, so I get 12x to the 3rd plus the sine of x. Then step number 4 is I multiply dy du and du dx together. When we do that, we get 6u to the 5th multiplied by 12x to the 3rd plus the sine of x, which is technically the correct answer, but really when we write them, we should put our answer in terms of one variable and one variable only. So I substitute my u back in. I get 6 times 3x to the 4th minus cosine of x, because that's what my u was. And then that is to the 5th power multiplied by 12x to the 3rd plus the sine of x. Now you might be asking, is there an easier way to do these questions? And if you look at it, here are some examples that have already been done. I've got 2x to the 3rd plus 3x minus 2 to the 7th. The derivative of that is 7 times 2x to the 3rd plus 3x minus 2 to the 6th times 6x squared plus 3. And you could look at all of these, and you would probably notice that something is going on in every single one of them. And rather than having, you can look at it, you can pause the video now if you want, and then we can talk about it in just a second. But realize in every one of these problems, here's what's happening. I am taking the derivative of that exponent, and I'm moving it down in front. And then you'll notice the parentheses part stays exactly the same, and we just subtract 1 from the power. So I bring the 7 down, leave all of that the same to the 6th power. So again, the inside portion stayed the same. Then we multiply that by the derivative of the inside function, and that gets rid of that whole u substitution thing. Every single time, that's where it comes from, but we don't need to know that in order to be able to take the derivative. This cosine of x plus 3x to the 7th all to the 4th power. Notice I took the 4, I moved it down in front, the inside part stayed the same, and then I raised that to the 3rd power. But because I used that u substitution stuff, I had to find the derivative of the inside part as well, which in this case is negative sine of x plus 21x to the 6th. Same thing on this problem. The only difference is, the reason why this is so long at the end is I had to use the product rule between 4x and tangent of x. In reality, the formal definition of the chain rule is this. If I'm taking the derivative of a composite function, I take the derivative of the outside function and leave the inside function alone. That's what this f prime of g of x is saying. Then I multiply that by g prime of x. In other words, I take the derivative of the outside function, leave the inside function just as it is. Then I multiply all of that by the derivative of what's in the parentheses. Okay? And we'll just skip that one right there. So if I wanted to take the derivative here, if I wanted to know what dy dx was, we could still go through the u substitution thing and do all that, but we don't really need to. I notice that all of this is being raised to the 6th power, so I would just take the 6, leave the inside of the parentheses alone to the 5th power, and then I would multiply by the derivative of what is on the inside of the parentheses. So in other words, just the derivative of this, and I'm all done. I didn't have to do the u substitution. It made it a lot easier. We just have to realize that as long as we take the derivative of the outside function first, then the inside function will be totally fine. Here's another one, okay? I'm going to take the derivative of this, and we're done. That was way easier than how we started. Notice the entire thing is being raised to the 7th power. So I go 7 times 2x plus 3 cosine of x to the 6th power. Again, I brought the 7 down. I subtracted 1 from it. That's why it became the 6th power. Then I just multiply that by the derivative of what is on the inside of the parentheses. This is what is known as the chain rule. Okay? The chain rule allows us to take the derivative of these composite functions as long as, again, we just have to take it one step at a time. We need to make sure that when we take the derivative, we leave the inside part alone initially, then we multiply by the derivative of that inside part after we've taken that derivative. What we're going to talk about next when it comes to the chain rule is how we deal with trig functions, because that's usually where people get tripped up on the chain rule. But for now, hopefully this makes sense on how we would take these derivatives. If you have any questions, please let me know.